Hello and welcome to Earth Science, Lecture 9, Earthquakes. On April 25, 2015, Nepal experienced its worst natural disaster in over 80 years, when an earthquake, measuring magnitude 7.8, struck this mountainous region of South Asia. The quake killed nearly 9,000 people and resulted in injuries to more than 22,000 others. The shallow nature of the 50-second earthquake resulted in widespread destruction and triggered an avalanche at Mount Everest, claiming the lives of 19 people, including international hikers and guides. Numerous landslides throughout the region blocked roads and delayed relief efforts, and Nepal's capital reportedly shifted 10 feet to the south during the course of this event. An earthquake is ground shaking, caused by the sudden and rapid movement of one block of rock slipping past another, along a fracture in Earth's crust known as a fault. Most faults are locked, except for a brief, abrupt movement when sudden slippage produces an earthquake. Faults are locked because the confining pressure exerted by the overlying crust is enormous, causing those fractures in the Earth's crust to be squeezed shut. Earthquakes tend to occur along pre-existing faults, where internal stresses have caused the crustal rocks to rupture or break into two or more units. The location where slippage begins is called the hypocenter, or focus. The point on the Earth's surface directly above this hypocenter, or focus, is what we call the epicenter. So the earthquake occurs at the focus, and that location on the surface above that is known as the epicenter. Large earthquakes release huge amounts of stored-up energy as seismic waves, which is a form of energy that travels through the lithosphere and to Earth's interior. The energy carried by these waves causes the material that transmits them to shake. Seismic waves are analogous to waves produced when a stone is dropped into a calm pond. Just as the impact of the stone creates a pattern of circular waves, an earthquake generates waves that radiate outward in all directions from the zone of slippage. Although seismic waves energies dissipate rapidly before moving away from the source, sensitive instruments can detect these earthquakes even when they occur on the opposite side of the Earth. Thousands of earthquakes are actually occurring around the world every day. Fortunately, most are small enough that people cannot detect them. Only about 15 strong earthquakes, which is magnitude 7 or greater, are recorded every year around the world. The occasional large earthquakes that are triggered near major population centers are among the most destructive natural events on Earth. The shaking of the ground, coupled with the liquefaction of soils, wreaks havoc on buildings, roadways, and other structures. In addition, a quake occurring in a populated area can rupture power and gas lines, causing numerous fires. In the famous 1906 San Francisco earthquake, much of the damage was caused by fires that became uncontrollable when broken water mains left firefighters without water. So let's discuss what actually causes these earthquakes. Well, the energy released by volcanic eruptions, massive landslides, and meteorite impacts can generate earthquake-like waves, but these events are usually weak. So what mechanism produces a destructive earthquake? Well, as we have learned, Earth is not a static planet. Because fossils of marine organisms have been discovered thousands of meters above sea level, we know that large sections of the Earth have been moving and thrust upward. Other regions, such as California's Death Valley, exhibit evidence of extensive subsidence. In addition to these vertical displacements, offsets in fences, roads, and other structures indicate that horizontal movements between blocks of Earth's crust are also common. The actual mechanism of earthquake generation eluded geologists until H. F. Reid conducted a landmark study following the 1906 San Francisco earthquake. This earthquake was accompanied by horizontal surface displacements of several meters along the northern portion of the San Andreas Fault. To better visualize, imagine standing on one side of a fault and watching a person on the other side suddenly slide horizontally by about 10 meters to your right. What Reid concluded from his investigation is illustrated in the figure on the right and will be discussed with the bullet points on the left. Over tens to hundreds of years, differential stress slowly bends the crustal rock on both sides of a fault. This is much like a person bending a limber wooden stick, as shown in figure A and B. Frictional forces will resist this motion and keep the fault from rupturing and slipping. Note that friction inhibits slippage and is enhanced by irregularities that occur along the fault surface. So in other words, the two pieces of rock are just stuck together. At some point, however, the stress along the fault overcomes the frictional resistance, and the slipping initiates. Slippage allows the deformation or bent rock to snap back to its original position, where it was stress-free. A series of earthquake or seismic waves then radiate outward, as in images C and D. Reed termed this springing back elastic rebound because the rocks behave elastically, much like a stretched rubber band does when it is released. So here's a really fascinating image. So field studies determined that during this single earthquake event of the 1906 San Francisco earthquake, the Pacific plate moved as much as 32 feet northward, past the North American plate. And in this image, we're seeing an example of where it was offset by about 8.5 feet. So what you're seeing here is somebody's fence that was actually offset by several feet just because of this earthquake. And in the background, we see a grove of trees, basically, and these are aligned in straight rows. But you'll notice right along here in a diagonal cut, the perfectly aligned rows are no longer perfect. So an earthquake actually offset these two along the fault. So, the slippage that occurs along faults can be explained by the plate tectonics theory that we discussed previously, which states that large slabs of Earth's lithospheric plates are continually grinding past one another. These mobile plates interact with neighboring plates, straining and deforming the rocks along their margins. Faults associated with convergent and transform plate boundaries are the source of most large earthquakes. Most of Earth's strongest earthquakes occur along large faults associated with convergent plate boundaries. Along convergent boundaries, where one continent is colliding with another, the resulting compressional forces slice Earth's crust along numerous large thrust faults. The 2015 Nepal earthquake is one example of an earthquake generated along a thrust fault. The epicenter of the quake was located 50 miles north of the capital, where the Indian plate is advancing into the Eurasian plate at a rate of about 2 inches per year, driving the uplift of the Himalayas. When convergence entails the subduction of oceanic lithosphere under another plate, as we see in the figure on the right, the area of contact between the two plates forms an extensive fault zone called a megathrust fault that can be several thousand kilometers long. Along most subduction zones, these megathrust faults remain locked for decades or even centuries. As the subducting plate slowly descends, it drags and bends the leading edge of the overlying plate, sometimes producing a bulge on the ocean floor. Once the frictional forces between the two stuck plates are exceeded, the overriding plate snaps back into its original shape. This snapping back generates an earthquake whose magnitude depends largely on the size of the zone of slippage. So, as an example, megathrust faults have produced the majority of Earth's most powerful and destructive earthquakes, including the 2011 Japan earthquake, which was magnitude 9, the 2004 Indian Ocean earthquake, which was magnitude 9.1, the 1964 Alaska quake, which was magnitude 9.2, and the largest earthquake ever recorded, the 1960 Chile quake, which was magnitude 9.5. So basically this overriding plate gets bent down, and once the frictional forces are overcome, it just snaps back up and triggers an earthquake. Faults in which the dominant displacement is horizontal and parallel to the direction of the fault trace, that is, the line where the faults intersect Earth's surface, are called strike-slip faults. Transform plate boundaries, or simply transform faults, accommodate this type of motion between two plates. For example, the San Andreas Fault is a large transform fault that lies between the North American plate and the Pacific plate. Most large transform faults are not perfectly straight, nor are they continuous. Instead, they consist of numerous branches and small fractures that display kinks and offsets. Earthquakes can occur along any of these branches. So in this way, earthquakes are triggered slightly differently. Instead of a plate being pulled down underneath another, in this case we just have two plates sliding past one another, which can of course trigger an earthquake. The study of earthquake waves, known as seismology, dates back to attempts made in China almost 2,000 years ago to determine the direction from which these waves originated. The earliest known instrument, invented by Zhang Heng, was a large hollow jar containing a weight suspended from the top. The suspended weight, similar to a clock pendulum, was connected to the jaws of several large dragon figurines that encircled the container. The jaws of each dragon are holding a metal ball. When earthquake waves reached the instrument, the relative motions between the suspended mass and the jar would dislodge some of the metal balls into the waiting mouths of frogs directly below. So that would allow the direction to be noted based on where the ball was dropped. In principle, modern seismographs, or seismometers, are similar to the instruments used in ancient China. A seismograph has a weight freely suspended from a support that is securely attached to bedrock, as you can see on the right. When vibrations from an earthquake reach the instrument, the inertia of the weight keeps it relatively stationary, while the earth and the support move. So in this device here, the support, the base, and the paper, and this pole all will start shaking back and forth. But the little arm with a weight and a pen don't move at all. So this entire piece of paper will basically just shift back and forth, and we'll see the reading of our seismograph. Inertia can be simply described by this statement. Objects at rest tend to stay at rest, and objects in motion tend to remain in motion unless acted upon by an outside force. You have all experienced inertia when you have tried to stop your automobile quickly and your body continues to move forward. So at this point, please pause the video and go to the YouTube description or the link on the screen and take a look at the seismometer video. Note that you can stop the video after 1 minute and 18 seconds. The records obtained from seismographs, called seismograms, provide useful information about the nature of seismic waves. Seismograms reveal that two main types of seismic waves are generated by the slippage of a rock mass. One of these waves, called body waves, travel through the interior of the Earth. The other type, known as surface waves, travel only in the rocky layers just below Earth's surface, or along the surface. So you'll note there's a lot going on in this image here, and we will reference this multiple times. So for now, just understand that there are surface waves and body waves based on where they go along the Earth or in the Earth. Well, you'll also note on this figure that there's something called P waves and S waves. So let's take a look at each type. Body waves are further divided into two types, primary or P waves and secondary or S waves, and are identifiable by their mode of travel through intervening material. P waves are push and pull waves. In other words, they momentarily press or compress and pull or stretch rocks in the direction that the wave is traveling. This wave motion is similar to that generated by striking a drum, which moves air back and forth to create sound. Solid liquids and gases resist stresses that change their volume when compressed, and therefore elastically spring back into their original positions once removed. Therefore, P waves can travel through all types of material, that is solid, liquid, or gas. So a good example of how these work is to take a spring or a slinky, attach it on one end, and basically just pull your hand back and forth with the slinky. You'll see, even with your own eyes, that there's like a little darker band of the rings moving back and forth. So you're sending a wave back and forth in the direction of the wave motion. So this is very important. These are the P wave type of seismic waves, the ones that are compression waves. But we also have S waves. S waves shake the particles at right angles to their direction of travel. This can be illustrated by fastening one end of a rope and shaking the other end, as you can see on the image on the right. Unlike P waves, which temporarily change the volume of intervening material by alternately squeezing and stretching it, S waves change the shape of the material and transmits them. Because fluids, that is, gases and liquids, do not resist stresses that cause the change in shape, fluids do not return to their original shape once the stress is removed. Thus, liquids and gases do not transmit S waves. So in other words, P waves can pass through liquids and gas, but S waves cannot. So what we just looked at were the two types of body waves, but we also have surface waves. There are generally two types of surface waves. One type causes Earth's surface and anything resting on it to move up and down, much as an ocean swells to toss a ship. The second type of surface wave that we see on the Earth's surface moves from side to side. This motion is particularly damaging to the foundations and structures of our buildings. So at this moment, please pause the video and watch the seismometer video found in the YouTube description or at the following link. By examining a seismogram, you can see that another major difference among the types of seismic waves is their speed of travel. P waves, which you see here on the left of our image, P waves are the first to arrive at a recording station, followed by S waves, and finally, surface waves. Generally, in any solid Earth material, P waves will travel about 70% faster than S waves, and S waves are about 10% faster than surface waves. In addition to the velocity differences in the waves, their seismograph recordings differ in height or amplitude, which reflects the amplitude of the shaking that they cause. So you'll see here, P waves are relatively weak and early, S waves are in the middle, and then our surface waves leave a huge signature, which means they do cause a lot of ground shaking. Surface waves also retain their maximum amplitude for a longer period of time. As a result, surface waves tend to cause the greatest ground damage by shaking and hence, destroying property. One method used for the locating of an earthquake is to rely on the fact that P waves travel faster than S waves. The traveling waves are analogous to two racing automobiles, one faster than the other. The first P wave, like the faster automobile, always wins the race, arriving ahead of the S waves. The greater the length of the race, the greater the difference in their arrival times at the finish line. Therefore, the longer the interval of time between the arrival of the P wave and the arrival of the S wave, the greater the distance to the epicenter. So let's go ahead and take a look at this image here on the left. So we can see P wave, S wave, surface wave. So we just said that the longer the time is between P and S waves, the further away it is. So just by looking at this, we can figure out which city is the furthest away out of the three for an earthquake of this type. And that would be whichever one has the more space between P and S waves, so that seems to be Nome, Alaska. So this figure here shows three simplified seismograms for a sample earthquake. Based on the P and S wave intervals, we can say again that Nome, Alaska is the furthest away. So this becomes important because we're going to be using a time travel graph. What this shows is each type of wave, P wave and S wave. Note that time is vertical on this graph and distance is horizontal. So because P waves are slower than S waves, it will always be lower than an S wave in terms of the time elapsed between it occurring and you recording the shaking of the ground. But because it's always slower, they get further and further apart. So in the beginning here, we're talking a difference of maybe a minute and a half between P and S waves. But when you get all the way to the end, you're now talking about 1, 2, 3, 4, 5, 6, maybe about 7 minutes between the P and the S wave. So distance will allow us to figure out how away an earthquake is if we're careful. Upon using the sample seismogram for New York on the last slide, we are going to use the travel time graph to determine the distance separating the recording station from the earthquake in just 3 steps. So we're given this sample and the travel time graph, and we're going to figure out how far away the station was. So step 1, using this New York seismogram, we can see that the time interval between the arrival of the first P wave and that of the first S wave is about 5 minutes. So here's the start on P wave, here's the start on S wave. That's 5 intervals or 5 minutes apart. Step 2, we now can go to the travel time graph and find the location where the separation between P and S waves is equal to the time we came up with, or about 5 minutes. So we're looking for anywhere on this graph where there's 5 minutes of separation between the 2 lines, which you find right here. So the final step of this, from that position, wherever you're located, draw a dashed line all the way straight down to the bottom, and that tells you roughly how far away the earthquake was. Well, the good news is we know how far away the earthquake was. The bad news is we can't figure out exactly where it came from unless we have at least 2 other stations. So we know the distance, but what about direction? Well, the epicenter could be in any direction from the seismic station. So just because we said, here's an example, that it was 2,750 miles away from Nome, Alaska, well, that means it could be anywhere along this blue circle with a radius of 2,750 miles. So that's why we need more data. So here the red circle shows it was within 2,300 miles of New York, and we see that the 2 circles intersect right here in the middle and up at the top here. Well, that doesn't give us a solid answer because there's still 2 options, so we need a 3rd circle as well. So using this method, which is known as triangulation, we can determine the location of an epicenter if we know the distance to it from 2 or more additional seismic stations. On a map or globe, we draw a circle around each seismic station with a radius equal to the distance that the station is to the epicenter. The point where the 3 circles intersect is the approximate location of the epicenter. Seismologists use a variety of methods to determine 2 fundamentally different measures that describe the size of an earthquake, that is, intensity and magnitude. An intensity scale uses observational property damage to estimate the amount of ground shaking at a particular location. Magnitude scales, however, which were developed more recently, use data from seismographs to estimate the amount of energy released from an earthquake source. Until the mid-1800s, historical records provided the only accounts for the severity of earthquake shaking and destruction. In 1902, Mercalli developed a reliable intensity scale which is still used today in a modified form. The modified Mercalli intensity scale, as developed using California buildings, is a standard. To more accurately compare earthquakes around the globe, scientists search for a way to describe the energy released by an earthquake that did not rely on factors such as building practices, with many varying considerably from one part of the world to another. As a result, several magnitude scales were developed. Magnitude scales, which were developed more recently, use data from the seismographs to estimate the amount of energy released at an earthquake source. In 1935, Charles Richter of the California Institute of Technology developed the first magnitude scale to use seismic recordings. The Richter scale is calculated by measuring the amplitude of the largest seismic wave. So here's our set of waves. You have P waves, S waves, and surface waves. So we're looking for the greatest magnitude or amplitude of our waves, which occurs probably right here. So we can read that amplitude out as about 23 millimeters. The time it took from the initial P to initial S is about 24 seconds in this image. And so we go to our graph and we put a dot where we find the amplitude of 23 millimeters, so right here. And with the time known, we can use the distance, which is, let's see, I forget where I put the distance, 220-ish. So if we know the distance is about 220 kilometers away, well then we can make a line between our 2 points and find out that we're crossing about a magnitude 5. So knowing the strength of the earthquake and how far away it is, we're able to figure out its magnitude. So this is because seismic waves weaken as distance between the hypocenter and seismograph increases. Richter developed a method to account for this. Theoretically, as long as an equivalent instrument is used, monitoring stations at different locations will obtain a similar Richter magnitude for every recorded earthquake. In practice, however, different recording stations often obtain slightly different magnitudes for the same earthquake, which is a result of the variations in the rock types through which the waves were traveling. So you'll get some practice with this in lab if you're in one of my courses, but you'll have to actually do an exercise like this where you determine the magnitude of an earthquake simply based on its seismograph record. So now that we at least have a quick idea on how the Richter scale was created, we can take a look at it in depth. So remember, it's dependent on not only the strength or energy released by an earthquake, but also by distance from the earthquake. So earthquakes vary enormously in strength, and great earthquakes produce wave amplitudes thousands of times larger than those generated by weak tremors. To accommodate this wide variety, Richter used a logarithmic scale to express magnitude, in which a tenfold increase in wave amplitude corresponds to an increase of 1 on the magnitude scale. Thus, the intensity of ground shaking for a magnitude 5 earthquake is 10 times greater than that produced by an earthquake with a Richter magnitude of 4. So each time you step up from one number to the other is basically 10 times stronger. The convenience of describing the size of an earthquake by a single number that can be calculated quickly from a seismograph makes the Richter scale a powerful tool. In addition, each unit of increase in Richter magnitude equates to a 32-fold increase in the energy released. Thus, an earthquake with a magnitude of 6.5 releases 32 times more energy than the one of magnitude 5.5, and roughly 1,000 times more energy than a 4.5. A major earthquake with a magnitude of 8.5 would release millions of times more energy than the smallest earthquakes felt by humans. Seismologists have modified Richter's work and developed other Richter-like magnitude scales. Despite its usefulness, the Richter scale is not adequate for describing very large earthquakes. For example, the 1906 San Francisco earthquake and the 1964 Alaskan earthquake have roughly the same Richter magnitudes. However, based on the relative size of the affected areas and the associated tectonic changes, the Alaska earthquake released considerably more energy than the San Francisco quake. Thus, the Richter scale is considered saturated for major earthquakes because it cannot distinguish among them. Despite this shortcoming, Richter-like scales are still used because they allow for quick calculations. Okay. So, as the energy released by earthquakes travels along Earth's surface, it causes the ground to vibrate in a complex manner involving up and down as well as side-to-side motion. The amount of damage to human-made structures attributed to the vibrations depends on several factors, including 1, the intensity of the earthquake, in other words, how strong it was, 2, the duration of the vibrations, 3, the nature of the material on which structures rest, and 4, the building materials and construction practices of the region. The intense shaking of an earthquake can cause loosely packed waterlogged materials, such as sandy stream deposits or fill, to be transformed into a substance that acts like a fluid. The phenomenon of transforming a somewhat stable soil into mobile material capable of rising toward Earth's surface is what's known as liquefaction. When liquefaction occurs, the ground may not be capable of supporting buildings, and underground storage tanks and sewer lines may literally float to the surface. During the 1989 earthquake in San Francisco's Marina District, foundations failed and geysers of sand and water shot up from the ground. Evidence that liquefaction had occurred with enough during the 2011 Japan earthquake, for example, to cause entire buildings to sink several feet. So here you can see an example of a Japanese region that was struck by an earthquake. The ground was liquefied, and you don't even see the building necessarily falling over. It actually sank. You can probably tell, even though it's cut out from this front building, that some of this building is in the ground. So it acts as a fluid. So I have two videos here that you should watch. The first one is just a quick animation and a demonstration of liquefaction. The second one is a pretty terrifying, but to me, one of the most incredible videos ever taken, in which someone is riding out the liquefaction process of an earthquake on top of their home while everything is sliding around them. All right, well, the last thing to discuss for this lecture on earthquakes are tsunamis. Major undersea earthquakes may set in motion a series of large ocean waves that are known by the Japanese name tsunami, or also known as harbor wave. Most tsunamis are generated by displacement along a megathrust fault that suddenly lifts a large slab of seafloor, as you see in the image here. Once generated, a tsunami resembles a series of ripples formed when a pebble is dropped into a pond. In contrast to those ripples, however, tsunamis advance across the ocean at amazing speeds of about 500 miles per hour. That is, about 4 times the speed of a commercial airliner. Despite this striking characteristic, a tsunami in the open ocean can pass undetected because of its high height. Amplitude is less than about 3 feet, and the distance separating the crests can range from 60 to 425 miles. However, upon entering shallow coastal waters, these destructive waves feel the bottom and slowly but surely cause the water to pile up. A few exceptional tsunamis have approached 65 feet in height. As the crest of a tsunami approaches the shore, it appears as a rapid rise in sea level with a turbulent and chaotic surface. It usually does not resemble a breaking wave. The first warnings of an approaching tsunami is often the rapid withdrawal of water from beaches, which is the result of the trough of the first large wave preceding the crest. Some inhabitants of the Pacific Basin have learned to heed this warning and quickly move to higher ground. Approximately 5 to 30 minutes after the retreat of water, a surge capable of extending several kilometers inland occurs. In a successive fashion, each surge is followed by a rapid oceanward retreat of the sea. Therefore, people experiencing a tsunami should not return to the shore when the first surge of water retreats. So it's usually a draw for people. The beach is suddenly being drained of all its water. You want to go out and explore, but that's usually a sign of a tsunami coming because it's the dip or trough of the first wave coming, and then the peak or just the peak of the first wave is then coming after that. And this image here actually kind of shows that. You can see the waters have receded and you see all this muddy stuff on the bottom, but here comes the first wave. And at the top here, you see an image from the Japan earthquake of the first wave coming through and starting to spill onto land. Now, we're going to watch a video of that Japan earthquake. So I really recommend watching this video. I believe, if I remember correctly, it's almost a half hour long, but you definitely don't have to watch the whole thing. What I recommend is just jumping around and skipping to different parts of the video just to see how I guess chaotic and powerful these tsunamis can be. So I do include a disclaimer that the video can be depressing or distressing at times, because occasionally you might be watching like a helicopter view of people driving away from a tsunami that aren't fast enough, so it can be a little distressing depending on how you react to these sort of things. But still, I think it's very valuable to watch. So we'll actually end on this note. This is one of the few lectures in which I don't have any questions at the end. We will continue with this discussion in our next lecture and answer questions there. So, as always, thanks for watching and have a great day.